Okay, for section 7.1, we're going to be talking about points in ordered pairs. Ultimately, we're going to be working with graphing and functions in this section. But to do a lot of the graphing that we're going to deal with, we need to be able to understand ordered pairs and also how to plot points on the coordinate plane. So we'll start out with a couple of vocabulary words dealing with our coordinate plane that we've had quite a bit of experience with, algebra, geometry, and algebra 2. And we need to know some vocabulary words. First of all, the x-axis, that's the horizontal axis. The y-axis is the vertical, of course. Okay. And the point in the middle we call the origin. And negative numbers are shown to the left and below the origin, and positive numbers are right and up. Okay. The four quadrants that we see here are numbered as such. The top right is the first quadrant, second quadrant, third quadrant, and fourth quadrant. Now, what we're going to do is take a look at a couple of ordered pairs, okay, which are going to give us locations on the coordinate plane. Okay. So each point in the rectangular coordinate system corresponds to an ordered pair x, y. Okay. X first, y second. Okay. We're going to look at these two ordered pairs. We have -5, 3, and then 3, -5. And ultimately we want to be able to plot these on the coordinate plane. Okay. So there's an illustration here. Okay. And the first number in each pair is called the x-coordinate. It denotes the distance and direction from the origin along the x-axis. So what we would do for -5, 3 is we would start at the origin and we'd go 5 to the left. Left because it's negative, 5 because that's the value of the number. The second number, the y-coordinate, denotes the vertical distance and the direction along the x-axis or parallel to it. So ultimately, in this case, we're going to, again, start here because we already went -5 to the left, and then we're going to go 3 in the positive direction, which would be up, and then we'll have our point -5, 3. Similarly, if we have 3, -5, we'd go 3 in the positive x direction, which would be here, and then 5 in the negative y direction, which would be down here. And these 2 points would be our coordinates plotted in the correct locations. And ultimately, part of our work today is going to be doing that, plotting some ordered pairs in the correct spots on the coordinate plane. So here's another example of some points that have been plotted. We have -3, 5. Okay, if we go -3, 3 to the left, 5 up, that would be -3, 5. We have 2, -4. So if we plot 2 to the right and then 4 down, that would give us point B. C has a 0 in it. Let's see what that looks like. If we go 5, 0, that means 5 to the right, but then no up or down, so we would just stay on the x-axis at that point. -5, -3, we go 5 left, 3 down. Okay. 0, 4 with a 0 x-coordinate, that means that we're going to go nowhere in the x direction, and then just 4 in the y direction, so we'd be at 0, 4, right straight up above the origin. And then finally F would be the origin itself, which should have coordinates 0, 0. Okay. Now, what we're going to primarily focus on today, though, is graphs of equations. Okay. So an equation, the definition here of relationship between two quantities can be expressed as an equation in two variables, such as y equals 4 minus x squared. And what we're generally interested in with equations is their solutions. Okay. A solution to an equation in two variables is an ordered pair of real numbers which have the following property. When the x-coordinate is substituted for x, y-coordinate is substituted for y in the equation, we obtain a true statement. Okay. And ultimately, if we were to ask to graph this equation, the graph of that equation is the set of all points whose coordinates satisfy that equation. Okay, there are many different sets of numbers that would make this sentence true, and if we plot them all, we're going to get a graph of that particular equation. Okay, so let's see how that works. So in our case, if we look at the graph selecting integers for x, starting at -3 and ending at 3, okay, we're going to make an xy chart ultimately for this. Okay. So for each x value, we'll find the corresponding y. So we'll plug in the -3 into our equation. 4 minus -3 squared is 4 minus 9, which would give us -5. So we'd have one ordered pair that would make this sentence true. It would be -3, -5. If we plug a 2 in there, we're going to wind up with 0. -1 in there is going to give us 3. 0 gives us 4. 1 gives us 3. 2 gives us 0. 3 gives us -5. And with that said, we ultimately have a set of ordered pairs that we could draw. Now again, this is just 7 points that are on this graph. Okay, there are, again, an infinite amount of combinations of x and y that would make that sentence true, but if we graph 7 of them, then we can get a pretty good idea of what the graph looks like. Okay? So if we plot those points, which is down here on the next page, we plot these points, we get a parabola. Now again, we've had quite a bit of experience with parabolas when we've taken algebra and geometry and algebra 2, as I mentioned, so it shouldn't be terribly surprising that that was a parabola, knowing that we were given a quadratic equation. Okay? So carrying on then, we're going to look next at the definition of a function. Okay? A function is an equation in two variables that yields precisely one y value for each x value, and we say that y is a function of x. Okay? We're going to talk a little bit more about this definition in a minute, but before we do that, we're going to look at this idea of function notation. A minute ago when I had the equation y equals 4 minus x squared, okay? If we use function notation, we would write that as f of x equals 4 minus x squared. And as stated in here on our line 2 here, the notation of f of x is read f of x. So when I said that a minute ago, I said f of x equals 4 minus x squared. Now you'll notice that these two are essentially interchangeable. Okay, y and f of x are essentially the same thing. Okay, just like we have here, y equals f of x. Okay. So again, it's just the notation that we use because a lot of times we're going to deal with situations where we might have more than one function, and usually we let these letters out in front be the names of the function. So this is the f function, we might have a g of x, we might have an h of x, etc. Okay, and therefore we can differentiate them between one another. Okay. Now, one thing to make sure we're clear about here with function notation, if we were asked to evaluate a function, like let's say that we want to find f of 6 for f of x equals 4x plus 5. Okay. And all f of 6 means is that we're going to replace the x with 6 in both sides of the equation. Okay, so if I need to find out what's f of 6, I'm going to plug 6 into the equation that I'm given. And in our case, we'd have 24 plus 5, and we'd have 29. Similarly, if I were asked for h of negative 4, and I want to know what that equals, and I know that h of r, and keep in mind that h is the name of the function, r is the independent variable, so over here we should expect to have r's. And it really doesn't matter what letters we use for these functions. Okay? But if I want h of negative 4, then I'm going to go ahead and plug a negative 4 into the equation. And if I do the math on that, I'm going to get 16 plus 28 plus 2. And if I add those together, I'm going to get 46. So if I'm asked for f of something or h of something or whatever the function's name is, all that means is I'm going to plug in that number into the equation. Alright, so let's take a look at some graphs of functions next. So we're going to graph the functions f of x equals 2x and g of x equals 2x plus 4 in the same rectangular coordinate system. And what we're going to do is plot points, okay, as such, just like we did in the previous example. Okay, for 2x, we're going to take these points and we're going to plug them in there. Notice we used 5 points this time instead of 7. And both of these are linear functions, as we should recognize from algebra. When we put those in there, we're going to get the following ordered pairs. And from there, we can go ahead and graph those on our coordinate plane. And if we plot those points, we can see that we do, in fact, get two lines. Okay? We do see a relationship, hopefully, between these lines. They look like they are parallel. And that is a fact we learned in algebra, that if we have two lines that have the same slope with a different y-intercept, that they are, in fact, parallel. Okay? Now, let's get back to that definition of a function that we looked at a minute ago. Here we talked about the definition, and ultimately the best way to tell whether a relation, a graph of a, or any kind of equation, if we look at this graph, okay, what it boils down to is if a vertical line intersects a graph in more than one point, okay, the graph does not define a function y in terms of x. So we call this the vertical line test. So let's take a look at a few examples here. If we look at this graph, okay, we can see that if we were to draw a vertical line through it, that it would in fact hit it more than once at the same time. So this would not be a function. Whereas if we looked at B, no matter where we drew a vertical line, okay, it would never hit the function twice. So that would be a function. If we have a parabola, that is also going to be a function always. Whereas the sideways parabola would not be, because again, the vertical line would hit it twice. So in that sense, we can check by graphing, we can check and see whether or not we have a function. Alright, finally, let's take a look at a graph here, dealing with analyzing some graphs. So in this particular case, the graph illustrates the body temperature from 8 a.m. to 3 p.m. Okay, we have some different body temperatures, hours after 8 a.m., the temperature given, etc. So X is the number of hours after 8, Y is the body temperature, and we want to know what is the body temperature at 8 a.m. Well, at 8 a.m., remember, is time 0. That's our starting time. So we can see that the answer to that, of course, is 101. Okay. Part B, during which time period is your temperature decreasing? Well, decreasing means that our Y coordinates would be getting smaller as we go to the right. So it looks like the decreasing would be from 0 to 3. So our temperature would be decreasing from time 0 to time 3, which for us would be from 8 in the morning to 11 in the morning. And then part C, estimate your minimum temperature during the period shown and how many hours after 8 does this occur. And ultimately our minimum temperature, of course, we can see is right here, and that would be approximately 98.6. We'll say it's exactly the normal temperature, if you will. 98.6, we'll just say as a guess here, between 98 and 99. And how many hours does it occur? It occurs 3 hours after our starting time. And what time would that be? As I mentioned a minute ago, that would be time 11 a.m. A couple more questions regarding that same graph. During which time period is your temperature increasing? Well, we can see on this branch right here, we're increasing. We're going from 98.6 up to 100. Okay. And then B says part of the graph is shown as a horizontal line segment, which of course is here. And what does this mean about your temperature, and when does this occur? Well, it means between time 5 and time 7, which would be 5 hours after, which would be 1 o'clock. 7 hours after would be 3 o'clock. So between 1 and 3 o'clock, what happens to our temperature? It doesn't increase or it doesn't decrease, it stays the same. Okay, our temperature remains at 100 from time 5 to time 7. Okay. Alright, and then in part F it says explain why this graph defines a function y, or defines y as a function of x. Why is this a function? Because it passes the what? It passes the vertical line test. So since it passes the vertical line test, okay, we have a function.